Okay. Um, so before, let's see, where were we? Okay. Um, okay, so um, all right, so here we are, full screen, share screen in just a second. All right, so Chem 1330, day 2 out of, I think, let's see, 16 weeks, roughly 32, give or take one or two. So, after today, there's only like 30 more meetings. 30 more meetings of an hour and 20 minutes a piece, roughly. It's like 45 hours. Yeah, 45 hours. So in a blink, it'll be gone. And so what we want to do is make sure that we get we have this recorded so you guys can go back and review it and everything like that. But before we really get into what and build on what we had last time, I wanted to do a little bit of review from last time because if you remember last time, it wasn't so much. I mean, there was a little bit of chemistry, but a lot of it was this idea of drug design, this rational drug design, and that has to do with shapes. So we're going to talk about that a little bit. Then we're going to go back and talk about some of the high points from your chemistry class last semester or your first chemistry class. Now, these are basically the high points of what we will get into today. And so on all of the slides that follow, I'm going to be filling those out with these topics. Sound good? Okay. So the first thing that I wanted to get after was what we talked about last time with respect to the idea of what are the steps of drug design. And those key steps, those 5 key steps. First of all, we've got to find a molecule that interacts with a target protein. So you've got to have that target protein that you're kind of going after. And then you have to find something that fits into that target protein. After that, we have to test if that molecule works in cells. So this is like removing cells from an organism from if you've ever had your blood drawn or something like that. When you've had your blood drawn, what's taken up? Well, lots of red blood cells. So this would be like you do an extraction of blood cells, or maybe you take a liver tissue or something like that. You can isolate those individual cells from that organ system, and you can test this drug to say, well, does this molecule work in those cells? And then go on to say, all right, well, let's get one of those rabbits, for example, one of these animals, and test it in those animals. So that's what's known as our preclinical research. After that, this would be phase 3. This is like the most important part. And arguably, this is the part where, or the place where most drugs or most therapies basically get rejected. Because this is where we test those molecules in humans, where we say, okay, well, we've got this drug that's been designed that maybe is a positive drug for lowering blood sugar, for instance. It's really good for people who have diabetes. Okay, well, or it's theorized to be good for people with diabetes. So you test liver cells, and the results are positive. So smiley face. Then you get some rabbits, and those rabbits, you get them on a specific diet, or basically um, give those rabbits something similar to diabetes. And you test this drug in those rabbits, and lo and behold, it works for the rabbits. So that's a smiley face. And so now you've got this evidence that, okay, well, the drug that we've designed helps with the individual cells. Okay, so an individual liver cell, it's good. Then we give it to the rabbit, and it's good. So we've got two big hurdles right there that have been cleared. And then last but not least, we tested in humans. And this is where you'd have like, um, does anyone know the term for a drug or a basically to put it, for lack of a better term, a fake drug in any sort of uh, drug testing like this? There's whenever you're studying something, you give the actual drug to somebody and then you give the other drug. Somebody added to the chat. The placebo, exactly. The placebo. So you give that fake drug, that placebo, to another group of people. So you have this blind test where you've administered the drug to a population of people, and then you've administered the placebo to an equal population, and you say, okay, well, as it turns out, this drug is effective, or it's ineffective, or it's equally as effective as the placebo, which if something's equally as effective as the placebo, the drug, for all intents and purposes, doesn't do anything because that placebo is probably like sugar water or something like that. Okay, so that's our clinical development. Then, after that clinical development, the FDA reviews all of the data from steps 1 through 3 to determine if there's good evidence, and that good evidence was collected and analyzed properly to determine if the drug is safe and effective for humans. Now, like I said, this phase 3, that always seems like, oh, that's going to be a slam dunk. Either it works or it doesn't work. Well, it's not always that simple. It's not always, oh, it works for 100% of people. Instead, it might be it was, 70% effective for 75% of the population. You have to analyze that data. And that's what the FDA, one of the responsibilities of the FDA is. Then, so that's our FDA review. Step 5, the pharmaceutical company and the FDA continue to monitor. So the drug has hit the market. Hit MKT. It's hit the market. It's out there. People are, it's being prescribed by physicians. It's being utilized. Now let's make sure that drug is as effective as advertised, and there aren't any sort of negative consequences of taking that drug or using that drug. Okay, so can I get a thumbs up if these 5 steps sound good, or a thumbs down if you'd like me to go through any of those steps? Let's go with thumbs up for I'm good, and a thumbs down for could you go back over them? And then after that thumbs down, say, step 2 or something like that. Okay, I'm getting lots of thumbs ups. Okay. Thumbs up, thumbs up. All right. If you don't want to share your thumbs up, meet with me, shoot me an email and we can set up a time. But it looks like that's good. Okay. Now we're going to switch gears a little bit because this is our like basic process. This is our overview of how drugs are designed. And so, that's all good and well and everything like that. But in order to really get into drug design, we have to go back a little bit and we have to get a good understanding of chemistry. And in your first semester, your 1310 class, you got a little bit of an overview of the periodic table. You maybe talked about the design and organization of the periodic table. What we're going to do now is it's almost like think about 1310 as you got this bulk of material. Okay, so here's this wide range of material. Now we're going to go through and kind of filter it. And we're going to say, what are the important parts? What are the high points of this? What we are doing today is, I'm going to say high points of molecules plus atoms. And then we're going to use this ultimately for a good understanding of organic chemistry. Okay. Now, I always like the way that I think about things is I always think about things as like a hierarchy. And so what I like to do is I like to visually organize things and say that they're under an umbrella. And maybe it's because of hip hop superstar Rihanna and her song Umbrella. Isn't I think that's the name of the song. But what I'm going to say is I've got this umbrella or this domain, and I'm going to call it science. Now, under the science umbrella, there's a physics umbrella. Under the physics umbrella, or sorry, also under the science umbrella, there's biology. Under the science umbrella, and I'm not going to go too far into this, I'm just going to leave it as chemistry. Now, under the chemistry umbrella, there's a field known as organic chemistry. And then under both the chemistry and biology umbrella, there's a field called biochemistry. What I want you to understand and recognize about this, and actually, you know what I need to do is I need to change the placement of my organic umbrella. Let's say here, I moved it over a little bit. And then I'm going to have this umbrella have kind of an overlapping region with kind of an interface where biology and chemistry are. And there's some biochemistry and organic chemistry that kind of overlap one another. Now, with that in mind, when you think about chemistry, there's fields underneath the chemistry umbrella. There's physical chemistry, there's nuclear chemistry, there's others, but there's organic chemistry and biochemistry. With that in mind, there are some elements that are super important for nuclear chemistry. For instance, can anyone think of an element that might be important for nuclear chemistry? And my hint is internationally around the world, there are some countries that they will enrich this particular element, and that is always brought before the United Nations, and it's like, oh my gosh, this country is enriching this. Oh boy, what are they going to use it for a nuke, or what are they going to do? Uranium, absolutely right. Uranium enrichment is something that the United Nations and other organizations keep a close, watchful eye on and say, okay, is North Korea, do they have any uranium that they're enriching? How would they get that? So I bring that up because uranium is an element. So uranium is under the chemistry umbrella. But uranium isn't a super important element for biochemists. It's also not a super important element for organic chemists. So when you think back to, and I'm going to actually do a share of this. When we look at the periodic table, which I'm switching to right now, when we look at the periodic table, you see, oh, there are 118 elements. And I think it's fair to ask the question, and I remember asking this question in my first chemistry class, do I need to know all of them? And at that time, in that first semester chemistry class, the idea or the attitude was, yeah, you do. And then I was like, oh man, do I have to memorize them? And it was like, no, you don't have to memorize them, but you've got to be familiar with like the makeup of the periodic table. And not long after that, I took an organic chemistry class. And then I took a biochemistry class. And with organic chemistry and biochemistry, I'm going to show you what basically they did. We took the whole periodic table and we said, oh boy, that's a lot of stuff. Let's not worry so much about these elements. And then let's not worry so much about these elements. Let's not worry about these elements. Let's also not worry about these. Let's not worry about these. let's not worry about yeah, these. And actually, you know what? Let's not worry about these either. And I remember thinking, okay, okay, I can work with this. We've gone from 118 elements to, as chemist and biochemist, and what we are is kind of a hybrid of the two, to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 elements. Perfect. I can work with that. We've taken 120 of them and said, what are the 10 most important ones? So these are arguably your 10 most important elements as or for the purposes of drug design. Now, what we're going to focus in on is we're going to take these 10 and we're going to refer to these group or this group right here as halogens. So those 4 elements, fluorine, chlorine, bromine, iodine, we're going to refer to those as our halogens. Then we've got carbon, nitrogen, oxygen, phosphorus, and sulfur. And then last but not least, hydrogen. Okay, so thumbs up if you prefer to be familiar with 10 elements as opposed to 118. This is probably going to be a pretty close race. Okay, we got 1, 2, 3, 4, 5, 6, 7. Okay, so you guys prefer to know about 10 of them as opposed to 118. I can work with that, and that's what I think we'll do. So these elements right here are arguably the most important ones for drug design and arguably for biochemistry as a field. So when you think about the periodic table, think about it as, yeah, there's 118 things on there, but I don't really need to worry too much about all of them. I need to know about 10 of them. Now, that's where we are here. Okay. Okay. I just got a private message. Yes, I will be uploading this video because it is recording. I'll upload it this evening. Yep, still recording. So anytime you have that question, by all means, go do what you need to do. I'll be recording. Okay, so those are our 10 elements. And, to simplify it, because we've got that group of 4 elements that are our halogens, what we could do is just look at this umbrella figure that I put together and say halogens plus carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So 4 elements, the 4 halogens, plus these other 6 elements. So that's essentially what we need to know. Okay, now when we look at each one of those, this is where I want to bring up subatomic particles. Let's jump ahead. Let's talk about subatomic particles. P-A-R-T. Oh, lose it. Particles. Now, I'll give you a little bit of a clue here. There's 3 of them. What are the 3 subatomic particles? And okay, neutron, proton, electron. I was close. I almost had to play a song from like 20 years ago that I would think is cool because it was popular. It was marginally popular 20 years ago when I was in college, but I think now it would just show my age, which I kind of just described to you. Okay, so neutrons, protons, and electrons. Now, these subatomic particles, they all have different charges. Does anyone remember what the charge of, or they may or may not have different charges. Does anyone remember what the charge of a neutron was? I'm going to make this like a table here. Charge. Exactly right. Neutrons have no charge whatsoever. Neutral is another way of putting it. What about protons? Positive. Perfect. And then last but not least, electrons. Where are those? Negative. Perfect. Okay. Now, these are important because what they allow us to do is come up with basically a model for what an atom looks like. And one of the things that I talked about last time, and I'm going to talk about again right here, is if you look at this little red cross here, you could also look at this and say that this is an X and Y axis. So this is 2 dimensions. So if I were to draw like a picture of a smiley face on that, I think everyone would agree that that image is like really well done. Took a lot of time, energy. I'm very passionate about art and the arts, but also you'd look at it and you'd say, okay, well, that's a 2-dimensional image because it's flat. It's going X and Y. Okay. Now, if I were to, oh man, if I were to go ahead and decide, this is really whenever I want to flex my drawing muscle, I would draw something like this. Draw it in green because I'm using multiple different colors. I'm using a diverse palette of crayons here. I think everyone would see that and say, dang, this guy can draw. Not only can he draw, but when I look at that image, well, it's on a 2D plane, but it looks like it's in 3 dimensions because we've got a background and a foreground. And I bring this up because whenever we think about an element and think about an atom of an element, well, really what we have is something that exists in 3 directions or 3 dimensions. So we've got our X, Y, and what's our last kind of plane here? The one that comes out of the page or up. Yeah, exactly, the Z plane. So whenever we're drawing something, when we're drawing an atom or thinking about an atom, I'm going to do some erasing here. We can think about that atom existing in 3 dimensions. Okay, and that one, now I can't erase that. So we can think about an atom that exists in 3 dimensions. Now, at this exact center point right here, I'm going to call that my kind of like origin place. What or which of our subatomic particles, could be 1, it could be 2, it could be 3 of those subatomic particles, which is at the exact center of this X, Y, and Z plane? And the answer to this is like this particular subatomic particle is almost always at that exact center point, at that intersection. Well, the one that's in the center, or one of them that's in the center, are your neutrons, which I'm going to draw my neutrons and I'm going to draw them in blue. And I'm just going to label it as an N. So neutron, neutron, neutron. I've got 3 neutrons there. Okay. The other subatomic particle that is in the exact center of an atom are your protons. So positive, 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 positive. Actually, I'll get rid of that one. And I'm going to draw another neutron. So I've drawn 4 neutrons and 3 protons. Now, what I need to add here is These have what's known as an atomic weight of 1 AMU. AMU is atomic mass unit. Electrons have 0 AMUs as their mass. So they are basically massless subatomic particles. Now, with that in mind, if we've got protons and neutrons in the middle, giving our atom all of the mass, or sorry, let me rephrase that. Our protons and neutrons, they come together to give our atom all of the mass. So when you look at this particular atom, we can piece some things together. What's the charge of this atom as it's depicted right now? If we count up all the neutrons, the charge is 0 because 4 times 0 is 0. 3 plus. You're absolutely right, Alondra. So we've got a charge of 3 plus. Okay. What about the mass? Four neutrons, 3 protons, 1 AMU. All right, perfect. 7 AMUs is the mass of this atom. Okay. Now, one thing that's important to know, and that will be important for this class, is understanding charges and being able to calculate that charge. Now, typically, an atom will have the same number of protons as it has electrons. Now, an important thing about those electrons is, let's go hypothetically and say that I threw down 1 electron. I'm going to do that electron in green. Okay, so if I have 1 electron with a negative charge, what do we know about positives and negatives? Do they repel one another? No, they're going to attract one another. So if we have 1 single electron, I'm going to go with, let's say, I'm going to make a box right here. I'm going to label this box A and label this box B. Where do you think a single electron is more likely to be? Answer is A or in B. Think about that single negative charge. Is it going to be in box A or B? Okay, I got 1 vote for A, another vote for A. Okay, so this is kind of a challenging question, a little bit of a tricky question. If there's only 1 electron, it's going to be pulled towards the positive cells or positive nucleus. So a single electron is more likely to be in B. Now, that's if there is only 1 electron. If there's 1 electron, it's going to be as close to the positive charges as possible. So I put that right there. Now, if there's a second electron, okay, now let's redo this just a little bit. We've got 1 electron there, and then I'm going to add a second electron in. That electron is going to be attracted to the positive charges. So the first electron and the second electron, they're both going to be attracted to the positive charges. What about if you have 2 negative charges and 2 negatives? Are they going to attract one another or are they going to repel one another? Think about this almost like the ends of a magnet. If you take identical ends of a magnet and you bring them together, well, are they going to get really close to one another or what? And maybe good terminology to use is repel or attract. Absolutely. If you have 2 negative charges, they're going to repel one another. So here's the thing. This electron right here has a couple of things going on. One, it wants to be close to positive charges. Well, you know what? So does this one. Close to positive charges. But also, they both want to be away from negative charges. So these two negative groups, or these two negative charges, these electrons, they want to be close to the positives, but they want to be far away from one another. Does that make sense? It's like they're both in love with the positive charges, but they hate each other. So what that means is that these electrons are in constant motion. So they're doing this kind of dance, like one electron gets close to the protons, and then the other one is kind of forced away. And then that one that's forced away comes back, and they just kind of swing like a pendulum. They're going back and forth, back and forth, back and forth. So that's the dynamic that's taking place with our subatomic particles. Now, this model right here is where we have 3 protons and 2 electrons. When we throw that third electron in, or when we throw a third electron in, well, the first 2 electrons right here, they're going to be able to kind of, it's almost like they, it's almost like they're third graders or something. And they say, well, I got here first. So we can be as close to the nucleus as possible. You, third electron, has anyone ever seen the movie Forrest Gump? Well, that third electron is Forrest Gump getting on the bus. These first 2 electrons are just constantly saying, seats taken, seats taken, seats taken. This third electron is Forrest Gump, and it's just like, well, I'm on the bus. I'm gonna be on the bus, and I'll just kind of be pushed outward. Okay. So when we get into elements with, like, let's say something with 30 electrons, we've got our Y plane, our X plane, and our Z plane. We've got our nucleus, where our protons and neutrons are, and then we've got some electrons as close as possible to the nucleus. Then we've got other electrons. These are referred to as orbitals or shells. Then, after that, you have these spaces that these electrons can be in. And this is one of the trickier parts about chemistry, is just kind of wrapping your mind around this. That's where your first 4 electrons are going to go. Your next 6 electrons are going to be in shapes that look like this. Here's an electron. Here's an electron. Here's an electron. Here's an electron. In your first semester class, you probably talked about the S, P, D blocks of the periodic table. Can anyone give a thumbs up that, yes, I remember that? Or those letters sound familiar? Or those blocks sound familiar? Okay, great. So that's all about, and this is really a tough thing about chemistry, is where these electrons are. So these electrons right here, these are considered to be p block electrons because they're in these kind of weird, like, clover leaf type of shapes. Now, this is important because this gives us basically a visual or an organization for where electrons are going to be found. This is important, and I'm going to jog back a second. We've talked about where electrons are. They're in the S, P, D, and does anyone remember the last subshell? It's a single letter. I'll give you a hint. It in the alphabet follows a vowel. Yes, Perfect. Well done. The f orbital. Okay. So where these electrons is super important for bonding. Okay. Now, jog back ahead. When it comes to bonding, there's two major types of bonding. There is ionic bonding, and there is covalent, and I'll say covalent / molecular bonding. The difference between these is in ionic bonding, electrons are given away. In covalent or molecular bonding, electrons are shared. Okay, so the difference between this is one, we're going to focus a little bit more on covalent or molecular bonding, where we're sharing electrons compared to where we're giving up electrons. And that's all because of the importance and the relevance to biochemistry. Now, when we talk about sharing of electrons, we have to talk about this thing called hybridization, or this phenomenon, we'll call it hybridization. Now, hybridization is whenever you hear about a hybrid, let me just share from my own personal thoughts. Whenever I hear about a hybrid, I think about a bicycle, a hybrid bicycle, something that's, sometimes people will refer to a hybrid as a bike that can kind of go in the city or can go on terrain. Something that's kind of like you took a mountain bike and you put city bike wheels on it. You took two things that were distinct and different from one another, but you merged them to make one thing. That's what I think about whenever I think about a hybrid. Now, hybridization, I always think about that as kind of like the process where you took those two distinct things and mashed them up together. So hybridization, when it comes to bonding, is where you combine different orbitals. And what that means is you do something like you would take an s orbital and combine it with three p orbitals. And you would make a hybrid orbital that is an sp3 orbital. Okay. There's also, you could do an s orbital combine plus 3p's plus 2d's. And you make an sp3d2 orbital. Now, the importance of this all goes back to kind of the 3D structure of an element or 3D structure of an atom. The reason or the theory is that an s orbital electron, so this idea of where these electrons are. So I'm going to jog back. I'm going to put a box around an s orbital electron. Let's say this one right here. This is an s orbital electron. An s orbital electron can only binds, or let me rephrase that, can only be in an s orbital. when shared. Okay. So long ago, whenever this theory was put together, it was basically, well, we've got these electrons that are being shared. This electron is in an s orbital, and it's being shared between these two atoms. Well, atom 1, that is sharing an electron from its s orbital, and atom 2. Atom 2 doesn't have any space in an s orbital. It only has space in a p orbital. So the idea is, okay, well, an electron can't go from an s to a p orbital, but I think what's happening is that this atom is taking an s orbital and a p orbital, or multiple p orbitals, and kind of blending them together to make a hybrid orbital. So that's the rationale behind it. Now, in terms of where do you see this play out? I think that the best way to think about it, and this is like, from my experience, this is like 20 years tested. When we talk about the hybridization of something, ask the question, how many things is the central atom connected to? Okay, so when you ask that question, how many things is the central atom connected to? We can look at a molecule and say, so here would be the example test question. What is the hybridization of CH or C, phrase that, of C in CH4? Question mark. Okay. So what's the hybridization of that carbon in this molecule of CH4? Now, to be able to answer this question, and many times what I'll do is I'll give you a structure and I'll say, what's the hybridization of this atom? And I'll point to that atom in a structure of a molecule. But for this, what we would do is we'd say, here is the structure, CH, H, H. So my question for y'all is, how many things is that carbon connected to? In this case, those things are hydrogens. So how many things is that central carbon connected to? Got 4. Yeah. So it's connected to 4 things. Now here's the little cheat code almost. Number of things plus hybridization. So here's your cheat code. If it's connected to 2 things, it is SP. If it is 3 things, it is SP2. If it is 4 things, it is SP3. If it's 5 things, SP3D. 6 things, SP3D2. So with that in mind, what's the hybridization of that carbon in CH4? SP3. Exactly. Then, if we were to go to something like this, just as an example, That's a molecule known as SF6. What's the hybridization of that sulfur? I'll give you a hint. It's not sp3. Perfect. sp3d2. Awesome. Okay. To jog back, this right here. Oh, I lost my. Like I said, I want you, or I think that it'd be fun for y'all to, you know, go to some of the sporting events, go to the Bobcats game, have a good weekend and everything like that. I'm not going to tell you what to do, but if right now you're thinking, I am at a crossroads. I know that I need to get a tattoo on my forearm, and I know that that tattoo has to reflect some important information from my Gen Chem or my Chem 1330 class. If you're at that point, I kind of think that that table's a good idea. Now, again, I'm not telling you that you have to do this. So in the event that you do it and that upsets somebody, that was your decision. I'm just saying this is like a really high value one. And it's going to be a like conversation starter for the rest of your life because people are going to be like, is that a good key for hybridization? And you'll be like, heck yeah, it is. sp3d2. That's something that has 6 elements around it, 6 atoms, or maybe 5 atoms in one lone pair of electrons. So this is going to be very valuable. But again, it's probably not going to be cheap. It might be a little bit painful, so maybe not the best idea. But this is hybridization. You're combining orbitals to make a hybrid orbital where electrons can be shared between different atoms. Now, in terms of bonding, we've got 2 big groups. We've got covalent or molecular bonding and ionic bonding. Those are our 2 big groups. How much time did we spend on ionic bonding? Not very much, because its electrons are given away. Covalent or molecular bonding is where electrons are shared. Now, that hybridization is how that sharing takes place. If we jump back a little bit more, the next thing that we need to talk about is this right here, electronegativity. Does anyone care to highlight or explain in the text or with their microphone, what is electronegativity? And or does anyone remember what is the most electronegative element? I'm going to go to a new slide here. So we'll start with what's the most electronegative element? Does anyone remember that? I'll give you a hint. It ends with INE. Fluorine. Perfect. Fluorine is the most electronegative element. Now, that's good, like trivial knowledge, but what is electronegativity? Well, electronegativity is the sharing either equal or unequal between, or sorry, sharing equal or unequal, I can say, of electrons between atoms. Atoms within a molecule. Okay, now to illustrate that a little bit more, one thing that you talk about in 1310 is you talk about Lewis structures. Now, you talk about Lewis structures, you talk about valence electrons, and if we take, let's go back to CH4. I'm going to draw a Lewis structure of carbon. Carbon looks like this. Hydrogen has a Lewis structure that looks like this. Okay. Now, carbon has those 4 electrons. Each hydrogen has 1 electron. And we always draw CH4 to look like this. These single lines between hydrogens and carbons represents a pair of electrons. Some people will draw CH4 like this. And what that's doing is that's showing this line right here. I've got to switch colors so that I can highlight it a little bit more. This line right here corresponds to those 2 electrons. So that's 2 electrons that are being shared between those atoms. Now, electronegativity is a measure of basically asking the question, does H or C want the electrons more? That's what electronegativity is. The sharing of electrons between atoms within a molecule. Now, electronegativity is it has numbers associated with it. It's quantitative. So you have a scale known as the Pauling scale. Of electronegativity that ranges from 0 to 4. I'm going to say 0.0 to 4.0. Our most electronegative element is fluorine. Now, carbon has an electronegativity of about 2.5, and hydrogen has an electronegativity of about 2.1. These numbers, the electronegativity numbers, I don't need you to commit to memory or anything like that. But what I want you to know about is, let's say that one of these hydrogens, I'm going to replace it with a fluorine. So I'm going to redraw this as CH4, and then I'm going to leave that as CH3, or this is CH3F versus CH4. Okay, now the difference between these is that CH4, I like to think about polarity and electronegativity, and I like to think about it almost like a game of tug of war. So in the center of CH4 here, we have, let's say, a 4-armed Incredible Hulk. And at each one of these points, we have, let's say, John Cena. John Cena is a strong person, and he's like a meme person. M-E-M-E, not M-E-A-N. So we've got Hulk right there versus John Cena. Now, we've got these 4 identical John Cenas. Those are our hydrogens. They're pulling with equal strength. When they are pulling with equal strength, where's the Incredible Hulk going to go? Where is that carbon going to go? Is he going to be pulled in any particular direction? That's my question. Is the Incredible Hulk or that carbon going to be pulled in any specific direction? Yes or no? No. Perfect. The Incredible Hulk or that carbon is not going anywhere because all of those forces that are pulling it, they're pulling in equal and opposite directions. So it's this game of tug of war where none of them are going anywhere. So these differences, so the fact that this is 2.5 and this is 2.1 really doesn't matter. Okay, now let's go over here. All of our hydrogens, those are still John Cena, but here what we have is Dwayne Johnson. The Rock Johnson. And I'm going to go ahead and say that he's stronger than John Cena because the electronegativity of fluorine is greater than the electronegativity of hydrogen. Okay, so now in this game of tug of war, is that carbon going to be pulled? I'll just use carbon versus hydrogen or fluorine. Is that carbon going to be pulled in any particular direction? Is it going to be pulled towards the fluorine or pulled towards the hydrogens? Yes, you're absolutely right. It's going to probably be pulled towards that fluorine because that fluorine is stronger. And what's really important to know about this is that these hydrogens, with those electronegativity differences, they're all kind of being like swung down in one direction. I love to think about this just as like a game of tug of war because then I can say like you've got a truck versus three Ford Festivas or something like that. That truck is going to pull with a greater amount of strength. So when we have something like this, you're going to Hulk there. We've got our CH4, we've got our CH3F. Well, with our CH4, this molecule is not being pulled PO or PULLED in any particular direction. So we say that this is non-polar because all of those forces are equal and they cancel one another out. Now, CH3F, this is a molecule that, well, it's being pulled three different ways and one fourth different way. So this is a molecule that is one thing, it's asymmetrical. This molecule is considered polar because of this asymmetry. We've got a polar molecule that is asymmetrical. We have a non-polar molecule that is symmetrical. So when we look at molecules, we can say if a molecule is polar or if a molecule is non-polar. In addition to that, we can look at a particular bond. And there are definitions that we don't have to, I'm not going to ask you explicitly about, but if the electronegativity difference, E negativity, is greater than GREATER than 0.5, that is considered a polar bond. So if the electronegativity difference is less than 0.5, then it's considered a non-polar bond. This right here, carbon to fluorine. Well, fluorine has an electronegativity of 4.0. The difference between C and F is 1.5. So that falls into this category of being a polar bond. Now, I'll add a little bit of a wrinkle to this. So this is considered a polar bond. It's considered, that is considered a polar bond. This is considered a polar molecule also. So polar bond and molecule. Okay. Now, if we look at something like this, CF, 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 CF. Our electronegativity difference here, this is 4.0 minus 2.5. This is a polar bond. Okay, so that's a polar bond. That's a polar bond. That's a polar bond. That's a polar bond. So we have 4 polar bonds. Now my question for you, thinking about symmetry versus asymmetry, and thinking about canceling out, my question for you guys is this molecule CF4? First question, does it have polar bonds? Yes, it does. Okay, so this molecule CF4 has polar bonds. Next question, follow up. Is this a polar molecule? No, it's not. Kai, you're absolutely correct. Okay, so one thing that I want you to keep straight is if a molecule has a polar bond, that does not necessarily mean that it is a polar molecule. Because in this case, we have four polar bonds, an equal number of polar bonds, pulling the exact opposite directions. And they basically cancel one another out. Doesn't matter how polar they are, they neutralize and cancel one another out. So this is because this is a symmetrical molecule. Now, if I were to make a change to this molecule and put, doesn't matter if I put chlorine there. Now I'm asking, is this a polar molecule? And I'll go ahead and say that Cl has an electronegative, F is 4.0, C is 2.5, and Cl is, let's say, 3.5 or so. Is this a polar molecule? This is definitely a trickier or a tricky way to think about this. Okay, this is a polar molecule. You're absolutely right, because whenever I replace that fluorine with a chlorine, that molecule has lost its symmetry. When it loses its symmetry, and I know you might be thinking about this and saying like, oh, well, if I, and this is how I definitely thought about symmetry of a molecule, I would say, oh, well, along this axis, it's perfectly symmetrical. But basically, we're looking at it and saying along any axis, is it asymmetrical? And so, sure, if you look at on this one, you cut it, but cut it down the middle. Oh yeah, it's perfectly symmetrical. But what about this way? Nope, it's not, because you've got two fluorines on this side, right here, and then you got a fluorine and a chlorine on this side. So it's asymmetrical. As soon as a molecule becomes asymmetrical, it's going to be a polar molecule. Okay, now let's jog back for just a second. So we talked about electronegativity. Then we got into kind of eased into polarity, talked about the differences between a molecule being polar and a bond being polar. And then last but not least, shape. Whenever I'm talking about shape, I'm really getting at symmetry. And I'm going to say yes or no. Is it symmetrical or is it asymmetrical? That's really my question. Now, I know that in your 1310 class, you might have talked about like bent or trigonal bipyramidal, those specific names for molecules and shapes of molecules. We're not going to go into that. What I want you to know about electronegativity is I want you to know the definition. Then I want you to know to be able to apply it to looking at a molecule and saying if this molecule is polar or non-polar. And then understanding that a molecule can have polar bonds and be a non-polar molecule. And that's all kind of dependent on the shape of that molecule. So, I mean, with that said, I'm going to go ahead and stop my recording. I'd also like to, I'll stop my recording and